Hello everyone, welcome. So today we're going to present to you how we have built a Rust smart contract fuzzer and the challenges and solutions we have encountered. So first, you might be wondering, why are these guys now showing me like a picture of a satellite? I thought this talk is about Rust smart contract fuzzing. But maybe some of you know this picture. It's the Mars Climate Orbiter, which NASA sent into space at 1998, and it failed shortly after. This was because of a simple unit conversion bug. So a very simple flaw that could have prevented by very simple testing beforehand, like unit test or fuzzing. And yeah, they lost about $125 million because of this. And the parallel here to smart contracts is that smart contracts often hold like hundreds of millions in them, and like just simple flaws could steal them, an attacker could steal them all because of a simple flaw. So you need to, throughout, like before deploying, test these kind of smart contracts really thoroughly. And that's what we are going to show here. So first to us, this is Kevin. I'm Daniel. We both work at security research labs as security researchers, and we both have a background in code insurance and blockchain security. So now onto some background information. First off, I already mentioned fuzzing a bit. What is fuzzing? So you can kind of imagine fuzzing is where you have some kind of fuzz target under test, and like for example, just a function which has input parameters, and you throw random input at it and observe it for undefined behavior. This could be crashes or some other logic flaws, for example. But oftentimes we don't want to have totally random input. We want to have some kind of less random input, and usually in the industry, coverage-guided fuzzing is used for this. So how coverage-guiding fuzzing works is that you have an input into the target, and while the target is executed, you track the code path it takes inside of the target itself to give this information back to the fuzzer and make some evaluated decisions based on this. So for example, mutate this input even further to reach even further into this target. And that's beneficial to reach further into the target because maybe there's some code there that triggers some interesting functionality which could cause a bug. But for this coverage-guided fuzzing to work, we need something called instrumentation. And instrumentation are just callbacks that are inserted into the target at compile time. So we have a compiler, let's say Clang or Clang, and this inserts some kind of callbacks into the target. Here on the right-hand side of the slide, you can see such an example where the compiler inserted something called sanitizer cough trace PC guard, and these act as like a callback back to the fuzzer to see, okay, we have executed this line or this basic block, and make some evaluated decision based on this. So now I talked a lot about the testing method here already, but what is actually our target that we want to test? And these are Inc. smart contracts. If you're not familiar with smart contracts, they're basically permissionless code that are deployed on a blockchain, for example. And maybe some of you are familiar with Solidity. So Solidity is such a programming language for it. But Inc. uses Rust for their smart contracts. And this is nice because developers can just use Rust, so they don't need to learn any other language to deploy these smart contracts. Inc. also has some other nice features like being cross-chain, having native support for cross-chain transaction, and being heavily integrated into the Polkadot ecosystem. On the left-hand side here, on the diagram, you can see an example of such an Inc. contract. As you can see here, it's written in Rust. But how do we then deploy it on the chain? So first we compile this Rust code, this Inc. code, to WASM, so WebAssembly. Then this WebAssembly blob is taken and put on the chain via something called pallet contract, which you can kind of just imagine as a module that handles this functionality. This WASM code is then executed on the blockchain via a virtual machine, the WASM virtual machine. But this virtual machine is sandboxed. So so there cannot be any information getting out or in of it, except if you provide some APIs for this. And Phink does provide some APIs for this. It's mainly get storage, set storage, and the most interesting for us, debug message. It also has some other APIs like upload contract, instantiate contract call message, which are also used to interact with the contract itself. So the contract has something called like public functions, which we call messages, that the user can interact with and then change the state of the chain. So now we present Phink, a coverage-guided fuzzer for Phink smart contracts.
Hi everyone. So this is like a demo of the tool that we made. So on the left you can see the fuzzer that will be spawned, and on the right the contract that will be fuzz. So to briefly explain what this contract does, basically it has some features, especially depositing token and withdrawing tokens, right? And there is a feature that is a cooldown, right? Let's say just a business logic. And this cooldown, basically, it's if a user does a withdrawal, then there is a cooldown and you cannot do a withdrawal afterwards. And it will be like such a issue, such a vulnerability, if at any point this will be like a user could find a way to do two withdrawal at some point, let's say, right? So sometimes reading the code can be like super complex and so on. But what if we could just create a property that says, okay, at any time of the contract, if there was a withdrawal made before and the user does another withdrawal, then there is a problem, right? This is called an invariant. This is a property that we want it to never fail. And so we could fuzz different messages, right? Try different messages, different state and so on to see maybe if at some point we can break these invariants. And spoiler alert, yes, there is a bug in the code here, especially if the amount is odd, then we set the cooldown to false, and this is a bug, right? So let's see if the fuzzer can catch it. And basically what you see here is that the fuzzer trying different possibilities, different origins. You have how fast it is on the top. And here we can see that there was one bug found. So we can just take the malicious seeds, the one that make the contract crashing, and we can simply execute it to see what happened. Okay, so what do we see here? We basically see that when the user called the simulate deposit with 10 tokens and then does withdraw of 10 tokens, because 10 is odd, then there is a bug and the user could do another withdrawal afterwards.
Okay, now that you know what Phink is, I'm going to present to you what the challenges were that we encountered while developing it. So we have four main challenges here, some of which are like general fuzzing problems and some of which are really specific to fuzzing Phink smart contracts. So the first one was probably the most challenging one, and is also the most interesting one, because as I said, like we need to instrument our target to enable coverage-guided fuzzing, but the Phink compiler doesn't support this. And the second challenge was creating some initial seed, so for our fuzzing campaign. The third one was getting some real state into our mock environment. And the last one, getting some coverage reports at the end of a fuzzing campaign. Hello? 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 Okay. So, as I said, the first challenge was getting Phink to work with coverage-guided fuzzing. The problem here is that usually you have these compilers like GCC, for example, which instrument the target, or like AFL minus Clang minus first, and they support this instrumentation out of the box. But the Phink compiler does not support this out of the box, so this insertion of the callbacks. So we could either fork the compiler, the Phink compiler, and implement this ourselves, or we could submit a PR upstream and then also somebody had to maintain it. The second challenge is, if we have this, As you can see here on the right-hand side of the slide, even if the Inc. smart contract is compiled, it is running inside this Fuzzing VM. And the Fuzzing VM is sandboxed. So we need some way to get this information, this coverage information we gathered, out of the sandbox. Because outside of the sandbox, we run something called AFL++, which is like the industry fuzzing engine. And we want this coverage data to end up in the coverage map of AFL++. So these are the two problems here. The second problem is creating some good initial seeds. So academia has shown that creating a good set of seeds, like some initial input that are not totally random, but like purposely generate like some good execution flows, have a very effective effective result on the fuzzing campaign. But creating these seeds manually is really time-consuming and cumbersome, so we need some kind of way to automate this process. And then the next question is, where do we automate this from? Where do we harness the seeds from? Like, we need some kind of reliable source. Our third challenge was, like, bootstrapping the state of the chain, of the smart contract. Because a smart contract is not a sole program that is encapsulated, but it interacts with a lot of different things on the chain. So, for example, other accounts or other smart contracts. So we need to have a way to enable it to get some state into this mock environment to be a realistic environment, and also interact with other smart contracts. And yeah, as I said, as I already teased a bit, we will probably have our own instrumentation. And for every good fuzzing campaign, you need some kind of feedback at the end. So this is usually done by a coverage report. And here on the right-hand side, you can see an example of OSS Fuzz, of a coverage report from OSS Fuzz, which is a project from Google, more specifically CGIF. And you can evaluate here after the fuzzing campaign what lines have been well covered, which aren't, and so on. So for example, these lines which are covered like over 4,000 times are well covered, like the lines that are only covered 10 times. At least we know here that the fuzzer can reach it. And then there are lines that are not covered at all, so we might want to improve on our fuzzing harness or input seeds. And yeah, now Kevin will present all of the solutions for these challenges.
Thanks. Okay, so we have been addressing to create Phink all these problems, right? Daniel said the most challenging one was the instrumentation part. The way we tackled this problem is trying to simulate how AFL++ compilers do it. So basically inserting some feedbacks, but in our own way. Then for generating initial seeds, we just leverage tests, right? Because when we think of it, when we have a program with some tests, the tests, they should represent a real world scenario. So this is amazing to create some seeds that the fuzzer can use afterwards. For the state, we have two things. The first thing is we give to the developers of the fuzzers, of the smart contract, to an interface where you can define a state, which is really easy to use, and this will really help the fuzzer to go onwards. We also enable cross-contract interaction so that the contract is not isolated, but can also, while being fuzzed, talk with the other contracts. And finally, for the coverage, we just made our own coverage report system. So users can generate reports for their fuzzing campaign. So let's talk about instrumentation now. We found two ways, both with pros and cons, to basically instrument our target. The first one requires the source code of the contract. So once we have the source code of our contract, we use a library, a Rust crate called sim, which allows us to properly parse Rust source code. And when we take our source code of the contract, we basically insert some feedbacks, some callbacks. Here we can see debug print ln, and that will basically give us which statement has been executed, right? So between each statement, we insert those callbacks. And you can see that for each of those debug print, there is a unique identifier, which we'll call afterwards the edge ID. So we take this contract, we compile it again, and then we just deploy it on the WASM host. And then the fuzzer will just execute some messages, and the feedback, the coverage will be extracted of the WASM machine. And we then have this function, redirect coverage, where we say, okay, create artificial if branches inside the harness and map it one-to-one to the feedback that you get from the contract, right? So if the contract sends, let's say, H1, H2, H3, then we will create those artificial branches here. And because our harness is compiled with AFL++, then AFL++ will understand, oh, I see that there is those new IDs, and it will update properly the coverage map. So now the question is, how does that debug print works, right? Because we said before, like, there is a sandbox thing, and how does that work? Well, this debug println that we see here, which is a Rust function, what it does under the hood is that it communicates with the WASM host. And if you remember, we talked earlier about this host API function, goes debug print, which allows us to communicate from the WASM blob, where we have the our bytes inside this debug print, and then pass it to our fuzzer, our harness. So that's really nice, but as I said, there is two problems here. There is it cannot be black box fuzzing, right? So if we don't have the source code, it doesn't work. And also, it's partially coverage guided, because let's say in our contract we have a function that calls, let's say, test. Okay, we have a contract. We have a function that that is, for example, in the standard library. Then we cannot instrument this, right? And this is an issue because then we can only have partial instrumentation. So for this, we find another way. We do basically in WASM instrumentation. And not only it allows us to do black box fuzzing, because we just need the WASM blob itself, the compiled version, we don't need the source code, but also we make it fully coverage guided. So how do we do it? It's really similar, actually. It's just we do it on a lower level. We also inject some callbacks. And here you can see, for example, 4 instructions. We have the first one that is 1000, it's just a pointer to the beginning of our edge ID map, right? So that points to like 1, 2, 3, 4, 5, and so on. Then we have 4, which is just the size of edge. Then we have the call 8. The call 8 is basically calling the function 8, which is the debug print. And then we have the drop instruction, right? And the way we do it is that we insert those callbacks on every control flow instruction. So it can be a branch, can be a loop, and all those kind of things, right? And then when we have this, we just do the same way. We deploy it on our WASM host. The fuzzer called different messages like withdraw, deposit, as we saw before. We get the coverage and send it to FL++. Okay, so now that we understand how we can get coverage of a contract and how we instrument it, it's nice to understand how do we pass from some bytes to some messages that are actually callable in the smart contract. Because FL++ only mutates bytes, right? That's how the fuzzer works. It just takes a bunch of bytes and mutate them, like use different mutators, flipping bytes and so on, and try to see if it crashes. So for this, we use what we call scale codec. So it's something that is used in the Polkadot ecosystem. It's really easy. We have a bunch of bytes, and we can transform into a Rust struct. And what will be our struct here? Well, it could be the origin, right? Who is sending the message? Bob, let's say. Then we have the transfer value, which is basically how many tokens do we transfer in a call. Then we have our payload, which is basically 2 things: the selector, so the message name, and the parameters of this. And then we just have some magic bytes here, the little asterisk that's used as the delimiter if we want to include different messages in one input. Right? So, for example, withdraw and deposit, let's say. Okay. So we understood how we can pass how can we transform some calls into some bytes. And now we can talk about this problem that we had, right? How to create good seed corpus, good corpus for the fuzzer without the user to do it manually, right? Because it's, talking from experience, it's something that can be sometimes really long, depending what you fuzz. So for this, we leverage the test. We basically take our contract and we parse the source code, also with the scene crate, and we insert those code that you can see here. Now, what does that code do? Well, it's pretty straightforward. It just takes the function name crushed with invariance, right? Then it happened to the parameters. Here you can see data. We encode it. And then, the same way we do it with the coverage, we use the debug print message to pass this data, those bytes, from the WASM blob to the host, basically. And then, pretty easy, we just run all the tests, and then we save all those bytes into the disk. And we have our seeds. Maybe we can see a demo of it, how that works in practice. So here we just run we make a copy, of the contract, because we're gonna modify it, so we don't want to modify the original version. We make a fork, and then we insert our callbacks, we compile it, we run all the tests, and then we save what we get from the debug print message to the disk. So here you can see the tests are passing, and we have some bytes here. So for example, if we execute this, the one seed that we saved, right, we can execute it and see what it was. And we can see that it was simulate deposit with 10, right? 10 tokens. So it means that the user made the test where at some point he called this function. Okay. Next challenge. So we said before that indeed we need to have a good state, right? So let's say, for example, we start to fuzz, but we want to transfer some token from Alice to Bob, but Alice doesn't have enough funds. Then we'll just stop at the beginning saying you don't have enough funds. That's a problem, because it limits our coverage, right? So, for this, we just made for the developers this thing where you can basically integrate his own state and say, okay, let's give some money to Bob, to Alice, let's mint some NFT, for example, let's create some validators and so on, so we have a good initial test. Now, the second thing to have a better state also is how do we enable those cross-contract calls, right? Because we often see some smart contract that depends on another smart contract, just for example for safe math. There is a lot of smart contract that requires some other smart contract to have safe arithmetics. And we also want the coverage of those smart contracts, right? This is really important. And basically it works natively. We just have to instrument also those smart contracts. We deploy it. And then we can just start the fuzzing campaign, right? And if we use the second instrumentation method with the in WASM instrumentation, then this is native, because by default the whole WASM blob will contain already the libraries. Okay, so last problem. How do we generate a coverage report so the user can see, okay, I see here there is like this part of the code is not covered, so maybe there is missing state, like there was some NFT that were not minted, for example, so we need to have something like this, right? For this, it's pretty easy. We just take all the seeds that we have, we run all of them, we extract the coverage ID, and because we can map the coverage ID to which line it corresponds, then we just need to make our HTML report that contains all the files, the Rust files, and then we can put in green, basically, the line that has been executed. If we want to push it a bit more, we could also put how many times we have been running those lines. It's not really difficult. We don't have time to do it, but it's not really difficult. So maybe a little demo of it. Here we run all the seeds, so we have a bunch of different seeds. Each of those seeds in a way adds some more feedbacks, some more coverage, that's why the fuzzer keeps it. And then we can just, all of those HIDs are put in a file called traces.cov. We parse those traces.cov and we map it to the good, to the file. So here we have the function that are covered in green and the rest are just some tests that we don't fuzz, of course. Okay, so we can conclude this presentation, see what do we have. And to conclude this, I think it's pretty cool to talk about some benchmarks. And what we can notice with those benchmarks is especially two things. First thing is this seed gen, right? So extracting the seeds out of the test, we realized that it has a lot of coverage. So anybody building fuzzers here, I really encourage you to create like some kind of, or at least building fuzzer engines at least. We encourage you to find a technique to do it maybe because it can be like really cool. We can see that we can almost double sometimes the coverage of the whole fuzzing campaign. The second thing interesting is the average speed. We switch from, at the beginning of the campaign, from 1,000 to 300 execution per second, and then we drastically slow down, sadly. And why? Because basically the fuzzer finds more and more coverage when it happens different messages, right, in one seed. Because, for example, if I want to withdraw, to stay on our example with the withdrawal, if I want to withdraw but there was no deposit before, it will stop at the beginning, right? But if you do the deposit and then the withdrawal will succeed, so we'll have way more coverage. So then we have those seeds that contains a lot of messages with a lot of coverage, but then we execute more and more messages, which is really heavy to execute. That's why over time we increase the speed. And maybe we can summarize the capacity of the fuzzer. So we have a forkless fuzzer, which is, this is pretty unique because usually we, for example, in FL++, there is, like, they have their own compiler that they need to maintain with LLVM every time. And, here we don't need to fork anything. We don't need to fork, for example, any compiler, like the Rust, the Ink compiler. We don't need to fork any libraries, neither like the node, the blockchain node, or neither the VM. So that's nice. We are also VM agnostic, at least with the first instrumentation function. Why? Because we do our instrumentation in the Rust code, in the Rust level. It means that in theory, with the Rust compiler, you could just compile your target into RISC-V or WASM, and we still have the instrumentation that we put before. And this is pretty cool because we realized recently that the people making Ink, they switched from a WASM architecture to a RISC-V architecture, and or RISC-V, I never know. And our fuzzer works by default, so that's pretty cool, at least with the first instrumentation part. Then we have a fully coverage guidance with the second instrumentation. And not partially anymore. And finally, we have the black box fuzzing. And why black box fuzzing is interesting, especially in a blockchain perspective, because the blockchain security heavily relies on the fact that everybody can check some stuff on the blockchain, right? And if you have a contract where we don't know really what it does, it's not something you want to interact with. And here, since the deployment of the contract is done on the blockchain, everybody can monitor the network, and it's like, oh, I see that a user deployed those bytes, this was enveloped into the blockchain, maybe I can just grab those bytes and fuzz it. And that's really nice for the community security. That's it. Thank you very much, everybody, for listening.